Welcome my friends, welcome to my next lecture. Now in my last lecture I talked about, of course, the notions of what is called smooth surfaces, oriented surfaces, okay, and like what is smooth surfaces, some example I have discussed, and then what is the parametric representations of smooth surfaces. So a couple of examples I have discussed. Now today's lecture I will talk about the notions of what is called scalar surface integral, because now I have the notions of smooth surfaces along with what is the parametric representation, okay. So now I am in a position to talk about what is called scalar surface integral, okay, that I will discuss at the beginning. So I'll define what do I mean by scalar surfaces integral, and then couple of properties, and then couple of examples I'll discuss. So that's the kind of motivation for today's lecture. And I think in my next lecture I will talk about what is called the notions of what is called this vector surfaces integral, right. So today I will talk about the notions of scalar surface integral, and then I will talk about vector surface integral, and then couple of properties. So as I said, today's lecture I will start the notions of what is called scalar surfaces integral. So that's the heading. So scalar surface integral over smooth surface. That now these notions of smooth surfaces I have discussed in my last lecture along with some parameterizations, and of course how to finding a normal vector. So those are some of the examples I have discussed. Okay, let's see what is the definitions of scalar surface integral. Now look at the notion scalar surface integral. That means I will talk about the surface integral for scalar valued functions. So it's clear from the notations that scalar surface integral, that means I will start with the functions, that means I will start with a scalar field, and then I will talk about what is the kind of notions of surface integral of this scalar valued functions over some smooth surfaces, okay. So that's the kind of notation. So look, so that's the kind of definition I am going to talk about, scalar surface integrals over smooth surfaces. So first we have to start with a smooth surface, or say piecewise smooth surfaces. Again, I am restricting myself in 3-dimensional Euclidean space, because at least in the 3-dimensional Euclidean space you will have the what is called pictorial way of looking at the surfaces. So that is more kind of explicit way you can see, so you can have the appropriate understanding for this, because if I go for 4-dimensional Euclidean space or higher dimensional Euclidean space, it's very difficult. However, whatever the notions I am going to discuss in R3, that same thing you can extend in the higher dimensional Euclidean space with an appropriate modifications, okay. So what you have to do, first you have to start with a smooth surface or piecewise smooth surfaces that I have already discussed in my last lecture, what is the definition of smooth surface along with the parameterizations. Then you see I am going to talk about what is called the notions of scalar surface integral. That means I have to start with a scalar valued function whose domain of definition contains my surface, okay. So therefore I am starting with a functions f, say from R3 to R, okay, and f has some domain, f is defined on some domain, and that domain should contains my surface gamma. So that is the first thing. Assume that f is continuous and bounded. Now I assume that means what? Means if I assume that my functions f is continuous and bounded on this surface S, then I can talk about what is called Riemann integral in that sense, okay. That's what. So if I assume that f is continuous and bounded on omega, or this is gamma, then I can define the notions of what is called scalar surface integral. Now how to do that, make a definition of scalar surface integral, like the Riemann integration I have defined. So look, so that's the picture I have said. So this is the kind of picture I somehow try to make it in 3 dimension. Look, so if I have a surface, so let it be this gamma, so this is the corresponding picture, so this is my gamma, right. So what we have to do now, if you remember like double integral, triple integral, what I have done, so I am starting with a, like if I have a curve or whatever it is. So now if I have a parameterizations of say like contour integration, if I want to talk about what I have done, if I take a contour, then the corresponding parameterization is there. So now if I want to take the partitions of my curve, I have to take a partitions of my interval, the parameterizations, which is a map from some closed interval AB to R3 or R2 or Rn, where I am to talk about the definitions of curve, or I want to talk about the curve sitting inside that space. So that means what? You have to take the partitions of the interval AB, and then it will correspond to a partitions in the corresponding curve in Rn, R3, R2, whatever it is. Same thing I will do here. I have a surface, right? It will have a parameterizations. Now if I take the partitions in the parameterization, that means parameterization is defined on some nice region in R2 and its value in R3, that means if I take a partitions in that region R2, the nice region, that means it could be a square, it could be a what is called circle, whatever it is, it's defined, maybe I think better to take a square. So that means A1 comma B1 cross C1 comma D1. So take a partitions there, and of course if I take a partitions in that nice square, in the R2, and if I use the parameterization, then parameterizations will induce a partitions in the surfaces, and that exactly the picture I have given. So you have a surface and it will have a parameterization, and parameterization is a map from some interval nice domain in R2 to R3. Now if I take a partitions in that domain, using that parameterizations I will have a partitions of my surfaces, and that exactly I have written. See, I have written this is corresponding, so this is the partition kind of my small pieces I have subdivide my surfaces, okay, and that the red one I have written as delta of sjk, okay. If S is my surface, so jk means j variable, that means I will have the partitions in the R2, that means I will have two variables j and k. So if I have a partitions in the R2 j variable and k variable, that means if I take a square, then it will induce a partitions of the surfaces, and that I am denoting as small portion of the surfaces is nothing but delta of sjk, okay. And what is my pjk? Pjk is a point, some point in the what is called small portion of the surfaces sjk. Now you can guess what I am trying to do. So now I have a partitions on the surfaces, I am taking an arbitrary point. So now the next part is that I have to take a Riemann sum, and then I have to talk about the Riemann integral. That exactly I am going to do. So this is the corresponding partitions of my surfaces. If I take the partitions of my interval or square in R2 using the parameterizations, it will give you partitions of my surfaces. Once I have that one, then you form the Riemann sum, that I am writing as Rs P comma F. What is P? P is nothing but the corresponding partitions I am talking about, and F is the functions. How do I make the Riemann sum? So now first of all, the small kind of portions of the surfaces, that means delta sjk, what you have to do, first you just calculate the surface area of this small portion sjk, which is like, I think it is delta sjk. If you write, maybe it's better to write delta sjk, okay. So that means a small portion of the surfaces, you just get the surface area of that small portion of the surfaces, and then what, pjk is an arbitrary point in that portion of the surface, so you have to just take the value of f at that pjk and then sum it over j and k. So in this way you can make the Riemann sum. And what is the scalar surface integral? Again, the scalar surface integral over my smooth surfaces gamma can be defined as, this is the notation, right? So integration double integral f over gamma d sigma, which is nothing but what you have to do, that just Riemann sum and take the partition goes to 0, norm of the partition, that means take a smaller very small portions of the partitions of the surfaces and take the norm of the partition goes to 0, and the corresponding Riemann sum, it will, if the limit exists, then the corresponding value is nothing but the surface integral of f, and that I am denoting as f d sigma over my smooth surface gamma, okay. So I think that's perfectly all right. So that means what is that? It's very nice. That means the way I have defined my contour integral, or the way I have defined my what is called double integral, triple integral, take a partitions of your things domain and then take a arbitrary point in the small sub portion of these partitions and make a Riemann sums and make your partitions finer and finer. That means the norm of the partition if goes to 0, if the corresponding limit of the Riemann sum exists, then I am saying that this is nothing but the value of the what is called scalar surface integral, okay. So that's exactly the definition. That means you don't have to remember anything. If you know the definitions of Riemann integral, then the same way I can have the notions of what is called scalar surface integral. So I'll start once again. So start with a smooth surface, start with the parameterizations, start with the functions f, which is a functions from some domain subset of R3 to R real valued functions, and the domain is contained your smooth surface, what is called this gamma, capital gamma, okay, and I am assuming that my function is continuous and bounded, so that I can also that a Riemann integral makes sense, okay. Once I have that, then since I have a parameterization of my smooth surfaces, so using the parameterizations, first you make partitions of your domain of the parameterizations, right. Parameterization is a map from some nice domain in R2 to R3. Suppose a nice domain is square, say A1 comma B1 cross A2 comma B2 to R3, it will be a smooth surface, and that is the corresponding parameterizations. I already discussed this kind of parameterizations for nice smooth surfaces. So you take the partitions in that square in the R2, it will induce, using the parameterizations of your surfaces, it will induce partitions of your surfaces, and it will be partitioned into small surfaces, and that I am denoting as delta sjk or sjk. taking an arbitrary point pjk from that one in that small surfaces sjk, and then you have to just make a Riemann sum. What is the Riemann sum? You just take the value of your functions f at the pjk, where pjk is an arbitrary point in that small portion of the surfaces sjk, and hit it with the surface area of this small portion sjk. Sum it over j and k. I am making the sum because it depends, because in the R2 you will have two variables, like if I have an interval like a1 comma b1 cross a2 comma b2, that means you take a partitions with the variable j, you take a partitions of this interval with the variable k. So therefore you will have double summation will be there. So therefore you make the sum over j from 1 up to n, k from 1 up to n, and you sum it up. So this will be a Riemann sum corresponding to the partition p and corresponding to the functions f. Now the next part is remaining, take and finer partitions, in other words norm p goes to 0. If this Riemann sum limit exists, then I am saying that this is nothing but the scalar surface integral of my function small f over this smooth surface gamma with respect to the surface measure d sigma, that I am denoting d sigma. Again in my next slides I will explain this, what is the meaning of this small portion of d sigma. Okay, so that's the kind of definitions of scalar surface integral, but there will be a formula. If I say that okay, take these functions, scalar valued functions which contains your smooth surfaces, then how to calculate the scalar surface integral, next couple of slides that I will discuss. Okay, so that's, I hope it is clear what is the definition of scalar surface integral over smooth surfaces. Now of course you can guess what will be the corresponding notions of what is called vector surfaces integral. Same thing will be there, but instead of now this time scalar valued functions, I have to start with what is called vector valued functions. Okay, that I will discuss in my next lecture. Okay, so this is a kind of picture I tried to explain, because in my next slides I will discuss the kind of how to calculate the scalar surface integral. For that this picture will be useful. For example, this is a very nice way of explaining, like look, this is the surfaces, right, and I have, this is my x axis, so this is my say x axis, this is y axis, right. So that means I have a what is called R2 plane, and I have a parameterizations, and with that parameterization this is the corresponding picture of my surfaces. Now how the surface integrals, look at this small grid, so that is nothing but the corresponding partitions. So if I have a partitions in my R2, that means in my this x axis y axis, suppose the parameterization is defined from the interval AB cross CD to R3, right. So now if I take a partitions of A to B and C to D, it will induce a partitions in the surfaces in R3. So this is the corresponding small grid. Actually this is a partitions in the R2, that means in the R2 domain where my parameterization is defined, and it will induce a partitions in my surfaces, and that I am giving x small grid. Okay, so like if I have a partitions in the x axis y axis, like say small, see, this is what, this is actually small del x, the small increment of x, and this is small increment of y del y, and suppose the corresponding I have a point, suppose this is rij, this is the kind of partitions in the R2 plane, that means rij. So that means this is, you can say if I take a partition, suppose this is my partition, say x0 x1 up to xn is equal to b, and suppose it will have a partition say y0 y1 up to ym is equal to d. Okay, so this is my c, this is d. Okay, then what will be the ijth partition? So rij, you can say this is nothing but I think xi minus 1 comma xi cross y j minus 1 comma yj. So this is I am denoting as rij. So this is a small portion of the partitions of the interval a to b cross c to d, and corresponding that small partitions in the R2, that means in the interval AB cross CD, it will induce a partition in the surfaces, and that I am saying it is nothing but Sij, and this is the black one actually I tried to draw. Okay, so this is the partitions. Now I want to talk about what is called the small portions of the surfaces, that means d sigma, then how to calculate my scalar surface integral. Okay, so notations I have written. So in the above picture, the surface is parameterized by the Cartesian coordinate as z is equal to gxy. So that's kind of surfaces and the Cartesian coordinate system, and the corresponding surface is like that. Okay, so if I have that one, now look in the next slides. Look, I want to now talk about what is called elemental surface area. That means the calculations part. What is the elemental surface area? That means you take finer and finer partitions, you take a more small portions of your surfaces, then that is somehow I can treat it as d sigma, this very small portions of your surface partitions, and that is I am talking about, if I talk about the area of this small portions of the surface, that I am saying as elemental surface area. Now how to calculate that elemental surface area, that I have explained now. Okay, so what we have to do, first start with a smooth surface in R3, that means it will have a parameterizations. What is my parameterization? My parameterization is phi. Okay, so that means phi is a map from some nice region in R2 to R3 whose component is x uv, y uv, z uv. Okay, there is a typos here, so it should be uv. So x, it is not x, not y, it should be u comma v. Okay, so therefore I have a smooth surface S, I have a parameterization phi, that means phi of uv, it will have three components x comma y comma z. So that means x comma uv, y comma uv and z comma uv. Okay. And what is my R? Of course, uv running over very nice domain R. So R is a simple convex region in R2. In particular, you can take AB cross CD. Okay. So now R is a simple convex region in R2. Then what I am doing, let R star be the subrectangle in a partitions of R containing the point u0 comma v0 in its interior. Okay. So now I have a region R. Now I can take a partitions of R, for example this one. So I have a, this is my R2, right? So I have a R. So now if I take a small partition, that I am denoting as Rij. So that this is a different way of writing. I am saying that, so R is the region in R2. I am saying that R star be a subrectangle in a partitions of R. That means you take a partitions of R, you take a small subrectangle. So partition means what? I am taking the partitions into smaller rectangles. So you take one of the arbitrary subrectangle, that I am saying that R star is the subrectangle in a partitions R which contains my point u0 v0. So that means u0 v0, it's a point in the region R. I have a partitions of R into small subrectangles. I am taking that small subrectangles which I denote it as R star which contains my point u0 comma v0. That's exactly I am written. So let R star be a subrectangle in a partitions R containing the point u0 v0 in its interior. So that means if I take, this is my point, say what is called u0 v0, and suppose this is my what is called R star. In picture it's like that actually. Okay. Now assume that the sides of R star are parallel to the coordinate axis and these sides are length del u and del v. Well, exactly the earlier picture, look at, suppose this is my R star. So as I said, so this is my R star. So this is my R star, and we see this is parallel to y axis, that I am denoting as del y. In the next language it should be I think del v, right? And this is del x parallel to x axis, that I am saying as del u, right? So that exactly I have written, you see. So that means I assume that the sides of R star, that means the smaller subrectangles which a portion of the partitions of my region R are parallel to the coordinate axis, that means I am just denoting as del u and del v. Okay, fine. Then what I want, I have a parameterization phi from R2 to R3, right? Now I am having all kind of informations in my what is called domain R2. Now phi is a parameterization, it's mapped from R2 to R3, and which will give you the surface. So therefore we want to find what? We want to find the surface area of my phi R star, that means the image of R star under the mapping phi. So I have a R star which has an interior point u0 comma v0. I have a parameterization phi. So therefore the image of R star under the mapping phi, which is nothing but the some portions of the surfaces will give you, and I want the surface area of that small portions. Okay, that exactly I have written. So we want to find the surface area of this object phi of R star, which is an elemental portion which I am denoting as S star of the surfaces S. Okay, so that's very nice. So now I have a parameterization phi on domain R in R2, taking a partition in the domain R, and I am taking a small sub partition that I am saying as sub rectangles R star of my partitions R. Then I am taking the image of this R star which contains my point u0 v0 inside as an interior point. So I want to take the image of R star under the parameterization phi, and that image phi of R star which I am denoting S star, which is a small portions of my surfaces or small partitions of my surfaces S. So that's what I am saying. So now we want to find the surface area of phi R star, which is nothing but S star, which I am denoting as, which is an elemental portions of my surfaces S. So that means I have to calculate the area of this elemental portions of my surfaces, which I am saying phi of R star or S star. Okay, how to do that? So let what we have to do. So now phi is a parameterizations of my surfaces, it's a map from R2 to R3, and u0 v0 is a point, interior point in R star. Okay, now let L be the derivative linear map phi at. So now what is phi? Phi is a parameterization, S is a smooth surface, so therefore my function phi is very nice, right? So therefore phi, if I take any point u0 v0 which is an interior point of R star, that means my function phi should be differentiable. If phi function is differentiable, then if since phi is a map from R subset of R2 to R3, That means since phi is nice because my surface S is smooth, so phi should be very nice, that is phi is differentiable at that point. So therefore derivative of phi at the point u naught comma v naught, it should be a linear transformation from R2 to R3, right, that we know, right, and that linear transformation I am actually saying this is L. So let L is a linear transformation from R2 to R3, which is nothing but the derivative linear map of phi at the point u naught comma v naught, and which is given by L u v, and which is nothing but this derivative of my phi at the point u naught v naught acting on u comma b, right. So phi is a map from R2 to R3, and I know explicit my phi na. So phi, what is my phi? So you can have this phi na, phi of u comma b, which is nothing but this, see, x u v, y u v, z u v. So therefore what is the derivative map? You can easily write it. So therefore what is my derivative? So derivative map, so that means yeah, so I can write it here. So derivative at the point u naught v naught, it's a linear transformation L from R2 to R3, right. Now if I get the matrix representation, what is the matrix? It should be a 3 cross 2 matrix, right. So 3 rows 2 columns. So now what is that? You can easily calculate it. So right, so 3 rows, that means it will have the like, so del x del u at the point u naught v naught, comma del x del v at the point x naught u naught, that is the first row. Then do the same, del y del u at the point u naught comma v naught, then del y del v, and finally you have del z del u and del z del v. So this is the 3 cross 2 matrix, right. It should act on u comma b, and that is the corresponding linear transformation. Okay. So therefore start with a L. I am saying that let L from R2 to R3 with the derivative linear transformation of my phi at the point u naught v naught, which is the corresponding what is called linear transformation. Now look, what I am saying is that surface area of my A star, what is that? A star is an elemental portion of my surface S. So I want to calculate the surface area of A star, and what I am saying is that this is actually equivalent to the surface area of portions of the tangent plane at the point phi u naught v naught. So okay, that's very nice. Why? Because you see, so look at the picture. This picture is, it tells you everything. So now suppose I have a point u naught v naught here. Okay, this is my point. So the corresponding, what is my phi u naught v naught? It will be point something like that, phi u naught comma v naught. And since phi is nice, so therefore derivative exists, phi is smooth, that means phi is S is smooth, surface is smooth, that means phi function is phi is differentiable. In fact derivative is also continuous. So if I take the derivative of phi at the point u naught v naught, it will give you a tangent plane, right. Now you see, this is the portion Sij, which is I am saying like a star, right. So this A star is a small elemental portion of my surfaces, and this is the corresponding tangent plane. Now you see, what is the elemental portion? You take a finer and finer partitions. If I take a finer and finer partitions, that means the area of the elemental portion A star of my surfaces S, which is exactly boiled down to the surface area of my tangent plane in that neighborhood. That's exactly I have written. Look, so surface area of A star, which is the elemental portion of my surface S, it is exactly very near to same as surface area of portions of my tangent plane at u naught v naught, because I am taking partition and partition very small. So that means the small portion, elemental portion A star of my surfaces, the area is almost same as the area of portions of my tangent plane at the point phi u naught comma v naught. Now how to calculate that one? That calculation, right hand side, this calculation I can do. How do I do that? Yes, look, the corresponding parallelogram portions L R star. So I have a R star which is a small subportions of my partitions of my region R. If I take the image under this R star with the linear transformation L, so the corresponding parallelogram portions L star of the tangent plane to A star at the point phi u naught comma v naught will have sides. And what about the sides? Sides should be L should act on del u comma 0 and L should act on 0 comma del v. So that means in the picture what is going on, suppose this is my del u. So I want a very small portion, I want to calculate the surface area of very elemental portion A star of S. Then I said that it is almost equivalent to a portions of the surface area of your tangent plane. So let's see that how to calculate the tangent plane there, because this is a corresponding del u in the x axis and length, and this is del v. So that means, so if I take, so that means all the points here actually del u, right. So now I have a linear transformation. So if I take L of say del u comma 0, so somehow it will give a what is called length of this one. This is the one, and if I consider L of 0 comma del v, that means this one, then it will give you some portion of this one. So now if I have a tangent plane, right, and if I have one side two-sided like this one, then I can get the area, because at the end of the day the portion of the area of the tangent plane is exactly or is almost similar to the area of the what is called elemental portion A star of my surface S. Okay, so I want to calculate the surface area of the elemental portion A star of my S, which is exactly or very near to the what is called surface area of some portions of the tangent plane. But I know how to calculate the surface area of the tangent plane, because it is nothing but, because to calculate the small portion of the surface area of my tangent plane I need to know the sides. And what are the sides? Because I have a linear transformation, L is there, because tangent plane is a derivative like what is called linear transformation. So that means you have to just take the image under your linear transformation L of the two objects. One is del u, that means del x comma 0, or that I am saying as del u comma 0, and other side should be L of 0 comma del b. So that exactly the case. So that means once you will have this and another this one. Okay, that's exactly I have done. So the corresponding parallelogram portion L r star of the tangent plane to A star, that means small elemental portion of A star at the point phi u naught v naught, will have sides as the vector this and this. Now once I have this vector, one side this, another side this, then what is the surface area of L A star? That's the small portions of your the tangent plane, and this is nothing but you take the cross product and take the norm of that. That's it. Okay, so therefore surface area, small surface area or portion of surface area of the tangent plane, which I am denoting as L of r star, which is nothing but almost equivalent to L. This is one side, this is another side. What you have to take the cross product and you just take the norm. So that is the corresponding surface area of your elemental portions of your what is called tangent plane, and which is same as the surface area of the elemental surface A star of my given surface S. Okay, so that means at the end of the day I have to calculate this object. Okay, so L is given, linear transformation is given, so that means I know how to calculate L of del u comma 0, then I know what is the L of 0 comma del b. I have to take the cross product and take the norm, and that will give you the surface area of L of r star, and which is nothing but the surface area of S star, which is nothing but the elemental portions of my surfaces S, and that I want to actually calculate. Okay, let's see. Look, so the vector L of del u comma 0, which equals del u times the vector represented by the first column 3 cross 2 matrix, this one. This okay, because what is my L? As I said, L is nothing but derivative of phi at the point u naught comma v naught, right? And it's a 3 cross 2 matrix, and I said so phi as a component I know na, phi is like that. So this is nothing but x u comma v, y u comma v, and finally z u comma v, right? So that is the my functions phi. So what is the derivative? So you can just write it. So del x del u at the point u naught comma v naught comma del x del v at the point u naught comma v naught. That is the first row. Then you have del y del u at the point u naught comma v naught comma del y del v at the point u naught comma v naught. And finally you have del z del u at the point u naught comma v naught comma del z del v at the point u naught comma. So this is the 3 cross 2 matrix. So what I want? So this should be L of, so I want the actions L of del u comma 0. And what is that? You just act 3. This is the matrix, L is there. So this matrix acting on this what is called del u comma 0. So what it will give? So this is nothing but, because this second component is 0, so that means only del u will come outside. So it will be exactly like that. So therefore if I write is, so this should be 3 cross 2. So that means I can write, so that means it is a 3 cross 2 matrix acting on what is called 3 rows. So yeah, so that means this should be del u comma 0. So that means it should be 3 cross 1 matrix. And what is that? Look, so I have this. So if I hit it first one, this one, so that means del u get multiplied, second one is del u multiplied, third one is del u multiplied, because the second component is 0. So that means it should be actually del u times your this component del phi del u. So that means you can write it as del u, and what is del phi del u? Del phi del u is nothing but you can have del x del u at the point u naught comma v naught, del y del u at the point u naught comma v naught, and del z del u at the point u naught comma v naught, correct, times del u. So in other words, you have the matrix, this matrix is given, you just hit it by what is called del u comma 0. Okay. So if I have del u comma 0, so this is hit it with this one, that means only del x del u times del u will survive. Then next one we hit it with this one, that means del y del u times delta of u will survive. Then finally del z del u in this multiplication, that means only del z del u at u naught v naught times delta of u will survive. So that means if I take the delta of u outside, so that means it is nothing but delta u times this vector, which is nothing but del x del u at u naught v naught, del y del u at u naught v naught, and del z del u at u naught v naught. Okay. So, this is exact expression of my actions of capital A on the vector what is called delta u comma 0. Similarly, you can calculate L of 0 comma delta b, because you know your matrix L, it is a 3 cross 2 matrix, again it will act on 0 comma delta b, this, so that means L should act on 0 comma delta v, right. So, again, so this portion will not survive, only this portion will survive. So, this is nothing but del phi del b, which is again, right, you can write it, this is what is called del x del v, del y del v, and del z del v. Okay. Of course, at the point u naught v naught it is there, I am not writing it here. Okay. Clear? So, now I have the explicit expression of this L of del u comma 0, L of 0 comma del v. Now, you have just, I have two vectors, you take the cross product. So, therefore, surface area of L of A star, which is nothing but L of del u comma 0 cross product del L of 0 comma del b, but I know what is this and what is this. So, therefore, surface area of this one, this is nothing but, so what will happen, this del u, these are scalar, right. So, del u del b will come out, so that exactly come out. So, that means I have two vectors, one is this vector and another is this vector. So, therefore, del phi del u at the point u naught comma v naught, which is nothing but del x del u at the point u naught comma v naught, comma del y del u at the point u naught comma v naught, comma del z del u at the point u naught v naught. This is one vector, cross product with del x del v at the point u naught comma v naught, comma del y del v at the point u naught comma v naught, comma del z del v at the point u naught comma v naught. So, two vectors, you take the cross product and do it. So, therefore, the surface area. So, surface area of the elemental surface area of the elemental portions of my surface S, which I denote it as A star, which is nothing but the surface area of the small portions of my tangent plane at the point what is called phi of u naught comma v naught, which is nothing but the surface area of L of R star, and this elemental surface area which I denote it as d sigma, and which is nothing but phi u cross phi b times du dv. Okay. So, phi u means what, del phi del u, and this is del phi del b at the point. So, u naught v naught is a one point I am taking, you can just take it arbitrary point. So, therefore, this is nothing but your small surface area of the elemental portions of my surfaces S. So, if I take a very elemental portion of my surface S, the corresponding surface area which I denote it as d sigma, which it turns out to be norm of. So, what I have to do, if I want to talk about the elemental surface area of my surfaces S, which contains my points say u comma b in the parametric representations. So, therefore, it actually turns out that the corresponding surface area, what you have to do, you just take the del phi del u and del phi del b, you take the cross product and small du dv. Now, you can guess if I replace this elemental surface area by this one, that means the surface integral can be converted to a what is called double integral. And it is expect the case, because I have a surface in R3 which has a parameterization phi, which is a map from some nice domain R2 to R3. So, it is expected if I somehow boils down to my scalar surface integral to the double integral, then I can calculate how to calculate the double integral, and therefore, you can calculate what is called your scalar surface integral. Okay. So, now at the end of the day, the conclusion is that elemental surface area, which is I am denoting as d sigma, which is same as norm of phi u cross phi b, because phi is the parameterizations and u v is the variable that you usually calculate phi u cross phi b, and you have du dv that is there, the corresponding parameterization variable u and b. So, once I have that one, that you see the next portion is that how to calculate scalar surface integral over smooth surfaces. Well, now I think you can calculate, because the target is done, right. The target is that I have the definition of scalar surface integral, and then I just somehow get the area of the elemental portions of my surfaces, which I denote it as d sigma in terms of the parameterization variable du dv. Now, I can just move to the corresponding double integral, and I know how to calculate double integral, then I can do that. Okay. So, look, so if I do that, then it will be more clear. Okay, look. So let's start with a surface S which is smooth or piecewise smooth in R3, and this is the corresponding parameterization. So, phi u v, which is x u v, y u v, z u v as the first, second and third component, and suppose your region is very nice, that means it is simple convex region in R2. So, now first you have to give what is my integrand, and what is the integrand that I want to integrate that functions over that smooth surfaces. Okay. So, first you have to start with a scalar valued functions from some domain in R3, and that domain should contains my nice surface or smooth surface S, and I assume that my function is continuous and bounded, so that Riemann integral makes sense. So that means I can take a partitions limit partitions taking finite and finite partitions, or norm of the partition goes to 0, the Riemann sum limit exists, and that I am saying as it is nothing but the scalar surface integral of my functions f over my smooth surface S. So therefore the corresponding scalar surface integral, that is nothing but denoting as this integration of f over the smooth surface S, and this is the d sigma is nothing but again area of the elemental portions of my surfaces. And you see I just get the relation that this elemental surface area of the elemental portions of my surface, which is nothing but norm of phi u cross phi b times du dv, right. So therefore the corresponding formula is surface integral of my f over smooth surfaces, that means that I am denoting as integration double integral of f over S d sigma, which I already discussed in term definition I have discussed in terms of Riemann integral, and that actually boils down to the corresponding double integral, which is nothing but you have to just take the functions f composed with phi uv, that the corresponding integrand will be there, and then you have an extra factor will be there, which is nothing but norm of phi u cross phi b. This you can also think about norm actually. Whenever I am writing mod, that means it actually means that it is the norm I am talking about, okay, and then du dv. So therefore if I calculate this double integral, then this is the corresponding what is called surface integral of my, or scalar surface integral of my functions f over smooth surfaces S. Okay. So now I think it is clear. So that means if I give some functions and if I give some smooth surfaces, and if I say that okay, calculate this scalar surface integral, then what you have to do, you just take the first you go for the what is called your, since surface S is smooth, so you have to have a parameterization, nice parameterizations, and parameterizations over some domain that is also smooth in R2. Okay, then what will you just get the parameterizations and then just calculate this double integral. That means you first calculate what is f of phi of uv, that functions, because you have functions f, you have the parameterization phi, you can calculate f composed phi at the point uv, that you can get it. Phi u, phi b, again parameterization is known, phi u you can get it, phi b you can get it, take the cross product, take the norm, you can get it, and over this region R also you know, because you know the parameterization, you just calculate this double integral, that's it. Okay. So this is the corresponding formula. So then I am writing here the unit normal. Now unit normal vector, you know, if I have a smooth surface S and if I have the unit normal vector, what is the formula? Unit normal vector at the point uv is nothing but of at the point phi of u comma b, which is nothing but phi u cross phi b divided by norm of phi u cross phi b. That is the unit normal vector that I already discussed in my last lecture. So once I have that in terms of n hat, you can write it. Okay, just keep it like that. This is the corresponding unit normal vector. Okay. So that means well, okay, here I am just writing here the unit normal vector n hat that I already discussed, which is nothing but phi u cross phi b divided by norm of phi u cross phi b. But this is the corresponding formula to calculate the what is called scalar surface integral. That means once I have the surface, smooth surface, and if I know the parameterizations, once I know the parameterization, that means I know the what is the corresponding domain of the parameterizations, what are the component of my surfaces, and then you just calculate the functions f composed phi at the point uv, then get the vector phi u phi b, take the cross product, take the norm, and just calculate the what is called double integral over the region R. Then this is the corresponding value of the scalar surface integral of my functions f over the smooth surface S, that I denote it as integrations f d sigma over S. Okay, I think one example, if I calculate explicitly, it will be more clear. Okay, look, so example evaluating scalar surface integral. So what is my function? So this is the functions integrand, which is given f of x y z is equal to x square, x y z is running over 3. Now look, so first is given that S is the cone, that the surface is given, which is the cone, that means z is equal to square root of x square plus y square, z running from 0 to 1. That means in the picture what will happen, I think this is the corresponding things, right? Z is equal to 0, it is a point, so that means it should be like that. Okay. So now compute the scalar surface integral of these functions over these smooth surfaces. Now we just follow the earlier steps. What is the step 1? First, once I have the smooth surfaces, first what you do, you go for the parameterizations of your smooth surfaces. Now this cone is already I have discussed in my last lecture, and what is the corresponding parameterizations? So this is the parameterization is phi of r theta, where r running from 0 to 1, theta running from 0 to 2 pi, that means it's running over the square, right? So in r variable I have a 0 to 1 and theta variable 0 to 2 pi. So that means what is your domain? That means 0 comma 1 cross 0 comma 2 pi. That's very nice domain, right, in the square. And what is the corresponding values in R3? This is R cosine theta, R sin theta, comma R. That's kind of parameterizations you already familiar with in my last lecture. So now I have the parameterizations of my cone, that is of step 1. What is my step 2? Once I have the parameterizations with the explicit components, then you can calculate phi r phi theta like phi u phi b. Like here I am calculating phi u phi b because I have the parameterization variable u comma b. Now here is the parameterization variable I am writing as r and theta. So you calculate phi r and phi theta, then take the cross product and take the norm. So that's you calculate it. So what is your phi r? So you can easily calculate. So phi r, which is nothing but del phi del r at the point r theta. What is this? So you just calculate the partial derivative of this function. So that means it should be cosine theta and then sin theta, and this is 1. Okay. And what about phi theta? So that means del phi del theta at the point r comma theta. What is this? So that means minus r sin theta comma r cosine theta and comma 0, because the only variable r I want to talk about the derivative with respect to theta variable, that will give you 0. Okay. Take the cross product. This is the formula. This is the first row ijk. So first vector should be cosine theta sin theta 1, that is this is. Third one is minus r sin theta, r cosine theta 0. This is a determinant formula I know. So phi r cos phi theta, if you just calculate it, it turns out that it should be r cosine theta I cap minus r sin theta j cap plus r times k cap. Okay. Now you just take the norm, which is the square root of the component square, means r square cosine square theta plus r square sin square theta plus r square. So this is by trigonometric formula, cos square theta plus sin square theta will be 1. So it turns out that the corresponding norm is nothing but square root of 2 times r. So this is the object, or you can say that this is phi r cross phi theta. So I am writing as mod, but it actually means that it is the norm I am talking about. Okay. So this is square root of 2 times r. So step t is done. Now use the formula. This is the formula you know na. You just last one you have to use the formula. Look. So step 3, evaluation of the scalar surface integral. That means this is the corresponding notations. What is the formula? Integral double integral over r. What is my r? This is my r, right? This is my r. So this is 0 1 cross 0 to 2 pi. Okay. Then f composed with phi at the point r theta. Now f you know, f of x y z, which is x square, and you know phi. So what is f of phi of r theta? You just calculate it. So you can just calculate it, right? So I have, yeah, right. So I have f of x comma y comma z, which is what? Which is x square, right? This is my x square. And what is my phi of r comma theta? Which is r cosine theta, r sin theta r. So r cosine theta, r sin theta, comma r. So what is this f composed phi at the point r theta, which is same as f of phi of r theta, and which is nothing but only the x square. That means it should be r square cosine square theta. Yes. So that's exactly the r square cosine square theta. And r region I know, r region is nothing but 0 to 1. This is the r variable, and this is the theta variable 0 to 2 pi. Okay. So that means the region is 0 1 cross 0 to 2 pi. Okay. This is the region. So therefore r running from 0 to 1, you see, and theta running from 0 to 2 pi. This is the corresponding f of f composed phi at the point r theta. Norm of phi r comma phi theta I have already discussed. This is square root of 2 times r dr d theta. Now this is very nice integration, right? The separation of variable. Take all the r functions one side, all the theta functions. So therefore just first integrate with respect to r. That means r from 0 to 1, r q dr. So it will give something, and then you have to integrate square root of 2 cos square theta. That is also easy to integrate if you perform the integrations. So it will turn out this is the corresponding value. Okay. So that is the way to calculate what is called scalar surface integral. So that means if I give a function and if I give a smooth surface, how to calculate? Couple of steps you have to follow. First steps, you just get the first parameterizations of your smooth surfaces, then calculate the vector phi u cross phi b or phi r comma phi, depending on what parameterizations variable you are using, and then use a formula that integrations surface integral of f over smooth surfaces is s d sigma. That means f double integration f d sigma over s, which is nothing but integrations over r. R is the region of your parameterization phi, and then f of phi composed r theta or u comma b times norm of phi u cross phi b, then du db. That double integral if you calculate it, then you can calculate the what is called value of your scalar surface integral. Okay. So I think another example, maybe I think next class I will talk about that. Okay. So this is one example. So now today actually I have just started with the definitions of what is called scalar surface integral, and I have defined in terms of Riemann sum. Then I shared that there is a formula to calculate the Riemann or that scalar surface integral in terms of double integral. To get that, one has to understand what is the minimal what is the surface area of the minimal portions of my surfaces S, that I have discussed, and it turns out that the corresponding d sigma is nothing but phi u cross phi b, if phi is my parameterizations with parameterization variable u comma b. So, you have to calculate del phi del u, you have to calculate del phi del b, you have to take the cross product, take the norm times du dp. So, once I have that one, then there is a formula to calculate what is called surface integral in terms of the double integral, and then one nice example I have discussed. In my next lecture, I will start with another example, and then I will talk about some properties, and then the new concept will come, what is the definition of what is called vector surface integral. I think I should stop here today. Next lecture, I will start with one more example of scalar surface integral, how to calculate it, and then I will start discussing on the definition of what is called vector surfaces integral. I think I should stop here. Thank you.